Okay. Now, let's discuss then how to move from the generation of a single random variable to the generation of an hydrograph. And the idea here is to assume that the hydrograph is generated by a process, which is the river flow generating process, including several random variables. One random variable per each time step. This is the underlying idea. So if one random variable describes the outcome of a number, the outcome of a given river flow value, what is then the hydrograph? The hydrograph is the collection of several numbers, is the collection of several river flow variables. And therefore the idea is to assume, I say again, that the hydrograph, let me depict an hydrograph here, is the result, is the collection of the outcome from several random variables. So basically, if the hydrograph is this one, you have a random variable here, which is qt star, a random variable here, qtw star, and etc. For each observation, you have a random variable. You may say, why can't we assume that all the numbers in the hydrograph, all the river flow observations are generated by one random variable only? So you may ask me, why do we need to do that? Because it's an intuition that if you put together several random variables, the situation becomes complicated. So you may say, why don't we use only one random variable? And I would say, look, it's clear that you can't do that. Because if you look at the observed hydrograph, what is this? This is the peak flow for this particular event. And it is the expression of a random variable, the outcome of from a random variable. Which means that, here we observed this value, but given that it was a random variable, we could have observed several different other variables here, several different other, values here. What we observed is just an outcome, but we could have observed other ones. And what regulates these outcomes? The probability distribution. So basically, I need a probability distribution to describe this random variable, and from which I can pick up only one outcome if I just want to simulate one value for the hydrograph, but I could pick up more. Now, if I go to another time step here, you see that the probability distribution is necessarily different, because we are in a different part of the hydrograph. We are on the recessing limb. We expect there a river flow that is lower than the peak flow. So this probability distribution will have an average that is different. And also the variability is different, because we know that the recessing limb has a reduced variability with respect to the rising limb. If I put together several observations of hydrographs for a river, I would see that here I have much more variability. Why is that? Because the rising limb is affected by the hydrology of the catchment and the variability of rainfall. In the recessing limb, it's only hydrology that is there. You don't have any more rainfall, which means that you have less variability. And also the steepness, or the slope of the rising limb, usually the rising limb is steeper. The recessing limb has a milder slope. And therefore, you see that necessarily you can't use the same probability distribution. You can't use the same random variable to describe these two outcomes. So we necessarily need to introduce, for each time step, a separate random variable if we want to simulate this process. And also there is another thing that you need to consider. For a random variable, the outcomes, the different outcomes are independent of each other. So think of tossing a coin. You toss the coin and then you make the next experiment, but it's not impacted by the previous result. Random variables, several different outcomes of random variables do not have any relationship with each other. And this is one important thing that you have to keep in mind. There is no relationship between outcomes, subsequent outcomes of one random variable. Now, let's suppose that we wanted to model this hydrograph by using only one random variable. But you see that if I look at these two time steps, there is a relationship between what I observed here and what I am observing here. You wouldn't expect here to find an observation here, because there is a relationship. And what is the relationship? It's a kind of memory of the catchment. The catchment has a memory. And therefore, if I go over the Po River and I look at the observation in subsequent days, there is a clear relationship. They are very similar to each other because perturbation in the Po River take a long time to take place. And therefore, you need, on the one end, to reproduce this relationship. So you can't allow that if you have a generation here, then the next time step you have another generation here. You can't allow this, you have to reproduce it. On the other hand, you can't reproduce it if these are treated as outcomes from the same random variable, because there is no dependence for the same random variable between subsequent outcomes. Instead, if you treat these two observations like outcomes from two different random variables, you can say, you can estimate, you can impose that the two probability distributions are very similar. And therefore, if you got here an outcome that is this one, when you go to the generation of this, if the two probability distributions are very similar, then you wouldn't take this one. You could take this, you could take this, or this, which is fine. And how do you obtain this result? By imposing that there is a relationship between the probability distribution that are subsequent. There is a relationship between the random variables. And this relationship is dictated by the hydrology of the process, which you reproduce by adopting, again, different random variables, different probability distributions for representing these two outcomes. And the way in which you introduce a relationship between probability distribution is by establishing a dependence between them, a dependence that reproduces the hydrological memory of the process. So I think I provided full justification for the idea of considering several different random variables for generating synthetic hydrographs. But still, you must be concerned by the fact that, defining so many probability distributions, looks extremely complicated. So what is the way for representing to get an overall representation of several different random variables by taking into account their relationship? The way is the use of a joint probability distribution. So in words, it's not complicated in words, because from the random variable, which is governed by one probability distribution, you turn to a collection of random variables, which is governed by a joint probability distribution. And the joint probability distribution allows for different single probability distributions, which are called marginal probability distribution at each time step. So the single probability distribution that compose a joint probability distribution are called marginal distributions. And indeed, if you see here the Wikipedia page for joint probability distribution, it says that in the study of probability, given at least two random variables, x and y, okay, let's forget about the probability space. These are definitions that we didn't discuss. I didn't want to introduce this notation, which is, of course, would be needed for a rigorous treatment, but I prefer to introduce a reduced number of definitions, the least number of definitions that I could. And basically, the joint probability distribution for xy is a probability distribution that gives the probability that each of xy falls in any particular range or discrete set of values. So basically, it tells you the joint probability distribution, what is the joint probability of getting these two values from two separate distributions. And you know, it's not really a huge complication. If it is only for two variables, you just have to define the two marginals, so the two probability distribution for the two individual random variables, and then you have to define their relationship. So it's not really complicated. The problem here is that you have many of them. It's not just two. If the hydrograph is, you know, 100 years long for daily data, how many random variables do we have to consider? So it becomes difficult to manage. It's not in principle a theoretical complication. It's an operational complication. So we understand that, you know, it's we need to simplify things, and we need to simplify this representation in order to reduce the number of random variables that is considered. So the idea is to find a way to simplify it by starting from the awareness that in principle at each time step you have a different probability distribution. Before I continue, let me provide now the definition, the formal definition of stochastic process, which is given here in a Wikipedia link somewhere here. And what is a stochastic process? The definition is very simple, but please remember it, because you know, it happens frequently. And let me say, it happened in the past frequently that when I asked at the exam, what is a stochastic process, the students were not really able to say that. And then the problem was solved when I started saying during the lectures, look, at the exam I asked for it. So, because it's very simple, the stochastic process is a family or a collection of random variables. That's it. And you can fully understand why this definition. So a stochastic process is a family of random variables. And you can fully, again, understand this definition, because it is what I need in order to represent the hydrograph. What did I say? I said that I need, you know, to represent it by using a collection of random variables. And this is precisely the definition of a stochastic process. So this is what we need. And you can find the same definition, hopefully, if you click here. And you see a stochastic process or a random process is a collection of random variables representing the evolution of some system of random values over time. You can say the evolution of some process made by random variables, random values over time. And you see here, this is the probabilistic counterpart to a deterministic process. Okay, let's forget about the continuation, but you are of course welcome to read it. And you know, when you see these Wikipedia entries, there is an introduction which is usually easy to read, and then you pass to a detailed description, which is summarized by the blue box, which becomes very technical. So you should become able to see the difference and to realize when it's the case for you to continue in the reading or just to read the introduction. In this case, you don't need to look at the details. And because, as I said, there are some concepts that I'm treating rigorously by providing all the fundamentals of the theory. And typically these are hydrological concepts. So when I talked about energy conservation, mass balance, I tried to be rigorous. For statistical and probabilistic concepts, I try to be efficient. And therefore I try to reduce as much as possible the technical details by providing only the technical details that you need for your application. So in this case, you know, when you look on the web at statistical definition of probability, my suggestion is just try to get the fundamentals, but don't look at the details because we didn't discuss them and I'm not going to ask them anyway at the exam. Okay, so again, we need to simplify things and because it is too complicated to deal with high-dimensional probability distributions. So the idea is, how can we make the problem simpler? The basic idea of the theory of a stochastic process is to check whether it's possible to apply a transformation to the data so that we can make the data following the same probability distribution, a unique probability distribution. This is the idea. So it's clear if we look at the hydrograph that, you know, it's perfectly clear that the probability distribution is time varying. Perfectly clear. The question is, can we make a transformation to these numbers in order to make the probability distribution identical? And what does it mean to make the probability distribution identical? It means that the random variables, the single random variables, are independent and identically distributed. Independent means that there is no relationship between this random variable, this one, and this one. So memory is removed from the numbers, not from the system, not from the physical process, because of course, you know, if you look at the catchment, it has memory. You can't remove the memory by the catchment. But from the numbers, it may be possible. So is there a transformation that makes, I say again, these random variables independent, removing the memory, and identically distributed? And this is called IID variables, independent and identically distributed. Is it possible? This is the idea. And if this transformation exists, or if we look for it, let's also look for a transformation that makes the data not only the random variable, not only independent and identically distributed, but also Gaussian. Why is that? Because the Gaussian distribution is easy to deal with. And I will explain to you later what I mean from a technical point of view, easy. So this is the objective. One, the objective of the transformation. And the transformation, they may be more than one. Is there a transformation that makes the data independent and identically distributed and makes the data Gaussian? Look, if the data are independent and identically distributed, I'm introducing a concept that is extremely important in technical application, then the process becomes stationary. What does it mean, stationary, and why this concept is important? From your intuition, you can understand what stationary means. It means that, independent and identically distributed. From a rigorous point of view, stationarity is a concept that applies to stochastic processes, and means that the joint probability distribution of an arbitrary number and an arbitrary selection of random variables within this process is not time varying. Technically speaking, what does this mean? It means that if I take this probability distribution and then this one, whatever collection of random variables within the process, and I estimate the marginals and their dependence, their relationship, in a word, the joint probability distribution, this is not time varying. If I make a shift of time, this is invariant. So if I consider the joint probability distribution f of x1, x2, random variable observed at time 1 and time 2, or let me use q to be clearer. This is equal in distribution to f of q1 plus delta t, q2 plus delta t. So you make a shift in time and the joint probability distribution doesn't change. And this implies that the variables are independent and identically distributed. Now, why stationarity is important? Because, the technical implications are indeed extremely relevant, because it means that you can use past observations to make predictions for the future. Because it means that any statistical relationship between past variables is replicated in the future. And now this opportunity concept is questioned in view of climate change. So if you look at the media, there is a debate that is ongoing on the representativity of past observations for making prediction for the future. Because of course, if you assume that climate changes, then the probability distribution of any hydrological variable, which is related to climate, of course, it changes. So basically, it means that you can't use past observation, you can't use past experience for making prediction for the future. And therefore, there is the say that we should shift towards non-stationary models. And this is an argument that is extremely important in the debate about climate change, which brought some scientists to state that there is a title of a famous paper that was published in Science. Science is one of the most prestigious international journals, and the title is "Stationarity is Dead." I think I already mentioned to you this debate. So basically, it's an ongoing debate. In my opinion, there is the relevant problem that if you assume that you should shift towards non-stationarity, we should make clear how to do that. Because otherwise we are engineers. We are engineers and we need methods, we need to make design. So no problem to use non-stationary models, but we should be told how to do it. Otherwise, if we don't have any non-stationary solution, we are forced to continue to use stationary solutions. And the debate on climate change is a bit delicate because climatologists, or let's say researchers in general, have an understandable tendency to exacerbate the negative effects. So basically, their mission is to point out what are the negative consequences of climate change. And it's understandable, I mean, because if climate change is indeed a concern, and therefore, in order to make the society aware, we need to convey concerns to the men of the state, to the public. And of course, you don't convey concerns if you say the quality of the wine is improved in France because of climate change. You must say that there are negative consequences. So there is a natural tendency, again, I understand the reasons, to exacerbate the negative effect. A famous scientist even declared that we need to say that disasters will occur if you want to get the attention of people. Otherwise, people continue to leave the car with the engine turned on, and etc. And but this has implications, and the implication is that that there is the tendency to say that methods are outdated, stationarity is dead, without proposing an alternative. As engineers, we need to be proposed an alternative. So I find it extremely dangerous the fact that there are media saying that stationarity is dead, that the retro period is an old concept, we need to use new methods, but at the same time we are not told what these methods are. The result is that our relationship with the stakeholders became more and more complicated. So I had some experiences in public consultation where one says, the risk of flood here is whatever, and they reply, yes, but there is climate change, and so I don't believe in your predictions. And this is really something that is, I think, limiting our capability to provide and agree an efficient, sustainable development. Because, the result is that everything gets stuck, and etc. So, let's go back. Is there a transformation that makes the data IID and Gaussian, therefore making the process stationary? Look, the process could be non-stationary. And in this case, it is. I mean, it's clear that an hydrograph is non-stationary. The probability distribution is changing. So it's clear that it's non-stationary. And so no problem with non-stationarity. I can accept it. Is there a probability distribution that makes the data stationary? Transformation. And the reply is given by the theory of stochastic processes. Stochastic processes, you can also define them, or let me say, stochastic models are made by a sequence of transformation that we devise to make the random variables forming the process IID, plus a convenient modeling of this now one random or one probability distribution. If the variables are IID, the probability distribution is 1. So you will not find this definition of stochastic model anywhere, but in my opinion, the stochastic model could be defined, again, as a sequence of transformation to make the random variable forming the process collected by the process IID, plus a convenient modeling for the underlying probability distribution. And I already anticipated that the convenient modeling is Gaussian distribution. And therefore, in introducing the stochastic models, which are mathematical representation of a stochastic process, the process is what is behind the numbers is what happens in the real world, and the model is what we use to reproduce the process. So our treatment of stochastic models will start with analysis of the behavior of the hydrograph, statistical behavior, and identification of transformations, suitable transformations to make the random variable IID. And again,